There is a sentence that physicists lean on when they run completely out of ordinary metaphors for what quantum experiments keep showing us. The sentence sounds almost like a trick or a piece of bad grammar designed to make you hesitate. The universe is not locally real, not merely counterintuitive, not just tricky to visualize, and not simply a puzzle that needs better math. Not locally real. That specific sentence was handed the highest recognition in science when the Royal Swedish Academy awarded the 2022 Nobel Prize in Physics to Alain Aspect, John Clauser, and Anton Zeilinger. They received it for a chain of experimental designs refined over more than 50 years. But those experiments didn't uncover a new particle or discover a hidden force. Instead, they methodically shut every single conceptual door through which our oldest, most comfortable picture of physical reality might have slipped through. When those doors clicked shut, an assumption that had underpinned human thought for centuries evaporated. Quietly, without fanfare, inside optics labs and underground fiber networks that almost nobody outside the field had ever heard of. Most public reporting on that award focused on the commercial upside. Journalists talked about entangled photons, secure messaging, and the long-term roadmap for quantum computing. The headlines were eager, and the explanations were fuzzy. Then, only a short while later, a collaboration involving researchers at Caltech and Google published findings claiming they had simulated the physical dynamics of a holographic wormhole across a quantum processor. A wormhole running on a circuit board. The story whipped around digital media for a few weeks before research groups stepped in to clarify what had actually been observed versus what had been hyped. And then in late 2024, Google introduced a quantum computing architecture known as Willow, built around a 105-qubit processor. In standardized benchmark tests, it completed a target computation in under 5 minutes, a task that would demand roughly 10 septillion years from the most powerful classical supercomputer operating on Earth today. 10 septillion years, a duration that exceeds the estimated age of the observable universe by a factor of roughly 1 quadrillion. These three occurrences, the experimental death of local realism, the simulated quantum dynamics of a holographic spatial bridge, and a processor outrunning classical physical limits by an unfathomable margin, are almost always framed as isolated stories. They get categorized as news items about hardware getting faster and nature getting stranger. But a single conceptual thread ties all three together. And that thread leads straight to a question theoretical physicists have been carefully tiptoeing around for nearly a century without wanting to announce it too loudly. What if space-time isn't the bottom floor of existence? What if space and time, the absolute stage where every event unfolds, the container holding every star, planet, and field, are not the fundamental bedrock of nature, but a secondary surface? A coarse, low-resolution projection emerging from something far deeper, far stranger, and entirely non-spatial. This is not a pitch for the simulation hypothesis, nor is it a claim that reality is an illusion that doesn't exist. Instead, the goal here is to lay out step by step what these experiments actually measured, what the underlying physics actually dictates, and where researchers who aren't chasing clickbait believe we actually stand. The unembellished truth of this narrative doesn't need hype. If anything, the cold reality is vastly weirder than any sensationalized headline could invent. To understand how we ended up here, we have to start where the trouble began. Not with an exotic particle in a modern lab, but with a picture of the physical world so remarkably successful that humanity forgot it was just a model. The foundation was laid by Isaac Newton, who constructed a physical universe that matched our deepest everyday instincts. Objects existed in absolute terms. They had fixed positions, definite masses, and inherent properties. Whether you were paying attention to them or not, those objects sat in space with their attributes intact, waiting to be noticed. The apple hanging from a branch was solid, red, and occupying a specific coordinate, regardless of whether anyone stood in the orchard to look at it. Furthermore, causes move through space at finite rates. Nothing could alter the state of a physical object instantly across a distance without a physical medium or signal connecting them. In principle, an ideal observer could stand completely outside the system and tally an exact, objective inventory of every single particle floating through absolute space along absolute time. It was a cosmic game of billiards, played on a table that stretched infinitely in every direction. This model was so overwhelmingly effective that it built our bridges, calculated industrial artillery trajectories, guided Apollo landers to the moon, and dispatched Voyager probes past the outer planets. It functioned so brilliantly for so long that its underlying assumptions became completely invisible. They ceased to feel like scientific hypotheses and began to feel like basic common sense. Much later, physicists gave those background assumptions a formal name: local realism. Realism, in this precise context, means that physical objects possess definite, fixed properties independent of whether an observation is taking place. An electron possesses an intrinsic spin orientation right now. A photon carries a specific polarization vector right now. These properties exist as objective facts about the world, totally indifferent to our detectors. Locality, on the other hand, means that physical influences cannot propagate faster than the universal speed limit. An event taking place at point A cannot instantly modify a physical condition at point B. Information, force, and causality are strictly bound by the geometric structure of space. Taken together, local realism feels less like a set of abstract physics postulates and more like the very definition of what makes something physical in the first place. Of course, things keep existing when we turn our backs. Of course, things can't affect each other without a signal traveling between them. Newton's mechanics felt so self-evident that it took nearly 200 years to find the first structural hairline fracture in the theory. That crack appeared in the 1860s when James Clerk Maxwell successfully synthesized electricity and magnetism into a single unified framework of electromagnetic fields. Maxwell's field equations produced a stunning prediction. Electromagnetic ripples, what we perceive as light, must travel through space at a fixed invariant velocity of roughly 300,000 kilometers per second. But fixed relative to what? In Newton's universe, space was an absolute, motionless background. If light moved at a set speed through absolute space, an observer moving along with that light ought to measure a different relative speed than an observer standing still. Yet every experimental attempt to measure this difference came up empty. The speed of light stubbornly remained the same for every observer, regardless of how fast or in what direction they were moving. Albert Einstein took this bizarre experimental reality completely seriously, and in 1905 built a new foundation of mechanics directly on top of it: special relativity. Special relativity warped Newton's neat universe in ways that shocked the scientific community. Time was no longer absolute. It flowed at different rates for observers moving relative to one another. Lengths contracted along the line of motion. Yet, special relativity strictly preserved locality. The speed of light remained the ultimate cosmic speed limit. Nothing in the universe could send a signal or exert an influence faster than light could traverse the spatial gap between 2 points. A decade later, in 1915, Einstein expanded this model into general relativity, reinterpreting gravity not as an invisible Newtonian rope pulling on masses, but as the literal geometric bending of spacetime caused by the presence of energy and mass. The universe was no longer a rigid table. Spacetime was dynamic. It could stretch, curve, flex, and ripple, yet it remained entirely local. Spacetime was still the fundamental stage upon which physical events unfolded, events that were objective, real, and completely independent of any observer. Einstein elevated this requirement to a core philosophical axiom known as the principle of separability. He maintained that if two physical systems are spatially separated from one another, they must possess independent physical existences. To Einstein, this wasn't just a preference for clean math. It was the absolute precondition for doing science at all. If an event happening on one side of the galaxy could instantaneously alter the physical reality of a particle on the other side without any physical signal traveling between them, then the idea of isolating a system in a laboratory to conduct a controlled experiment would completely collapse. He needed the world to be local, and he needed it to be real. He would spend the final 3 decades of his life fighting against a brand new branch of physics that insisted the world was neither. Quantum mechanics, which emerged during the first 30 years of the 20th century through the combined work of Max Planck, Niels Bohr, Werner Heisenberg, Erwin Schrödinger, Paul Dirac, and many others, was fundamentally uncomfortable from day one. It stopped describing particles as tiny, localized billiard balls with fixed coordinates and trajectories. Instead, it described them using mathematical wave functions, clouds of probability spreading out across space, indicating not where a particle was, but where a particle might be detected if an instrument intervened. When an instrument finally did intervene, the mathematical wave function appeared to instantaneously collapse down to a single, localized result. Prior to that measurement, according to the emerging consensus, the particle didn't possess a hidden, definite location that we simply hadn't mapped yet. It literally lacked a definite location altogether. In 1927, Werner Heisenberg formulated his uncertainty principle, proving that you could never simultaneously measure both the exact position and the exact momentum of a quantum object. Crucially, this wasn't a limitation of crude laboratory tools. It was a fundamental property of nature itself. The universe simply did not contain both pieces of data simultaneously. Pushing for extreme precision in a particle's spatial coordinate explicitly dissolved the definiteness of its momentum. They were complementary aspects of a single quantum state, and forcing one into sharpness automatically rendered the other indefinite. Schrödinger's equation, which governs how these quantum states evolve over time, is smooth, deterministic, and precise. Given the initial quantum state of a closed system, the equation tells you exactly what that state will look like at any future moment. The existential crisis is that the state it tracks is not a single definite reality. It is a superposition, a mathematical combination of multiple mutually exclusive physical possibilities, all evolving simultaneously. An electron fired toward a barrier with two thin slits doesn't pass through the left slit or the right slit. The mathematics and the physical measurements insist that its wave function propagates through both slits at once. The interfering waves on the other side determine the probabilistic pattern of where that electron will eventually strike a detector screen. If you fire electrons one at a time, very slowly, they still gradually build up a wave-like interference pattern on the wall. This double-slit experiment has been verified tens of thousands of times in laboratories around the world. The quantum formalism works flawlessly. Its calculations match real-world data to more decimal places than any physical theory in human history. The underlying horror for classical physics was that quantum mechanics seemed to demand two unacceptable things. First, that physical systems do not possess definite values prior to the moment of observation. Second, that when two quantum systems interact and become entangled, performing a measurement on one system appears to instantaneously dictate the state of the other, no matter how much space separates them. Einstein famously dismissed this feature as spooky action at a distance. He refused to accept that nature operated this way at a fundamental level. That refusal drove him to draft a paper that redirected the course of physics forever, even though the specific conclusion he tried to prove turned out to be completely wrong. The deeper you analyze the Newtonian picture, the more invisible assumptions you uncover. Absolute space, the fixed, unmoving, invisible stage on which everything occurs, has no direct observational signature. You can't scoop up a bucket of pure space, you can't point a light beam at it, and you can't attach an instrument to it. Newton understood this vulnerability. To defend his framework, he devised a famous thought experiment involving a rotating bucket of water. As the bucket spins, the water's surface curves into a concave bowl shape, climbing up the inner walls. Newton argued that this curvature proved the water was rotating not relative to the bucket itself, but relative to absolute space itself. 2 centuries later, the philosopher and physicist Ernst Mach challenged this conclusion. Mach argued that the water's surface didn't curve because it was moving relative to an invisible spatial grid, but because it was rotating relative to the combined gravitational mass of all the matter in the cosmos, the distant stars, planets, and gas clouds. In Mach's view, if you removed all the matter from the universe, leaving a totally empty void, the concept of rotation would become meaningless, and the water's surface would remain completely flat no matter how fast the bucket spun. Einstein was deeply inspired by Mach's line of reasoning. When he developed general relativity, he hoped to fully incorporate Machian ideas, showing that space had no independent existence apart from the matter and energy within it. Whether he fully succeeded is still debated among modern cosmologists. What Newton undeniably got right, however, extended far beyond his mechanical formulas. He firmly established the principle that the physical world operates under universal mathematical laws, that the precise mathematical relationship governing an apple dropping from a branch in an English garden also dictates the orbit of Jupiter around the sun. He established that natural phenomena can be mathematically modeled, and that localized, carefully measured experiments can reveal absolute truths that hold across the entire observable universe. These foundational principles are so completely embedded in modern scientific methodology that we rarely stop to analyze them. The assumptions of local realism weren't arbitrary philosophical add-ons to classical physics. They were the direct, natural consequences of trying to write local differential equations that explain what is happening here and now, purely in terms of physical conditions that exist here and now. Local realism followed almost automatically from that project. Quantum mechanics didn't just add a tiny correction to Newton's classical framework. It exposed the fact that the framework's most basic premise about how physical reality works was fundamentally flawed. In May of 1935, Einstein, along with two younger colleagues, Boris Podolsky and Nathan Rosen, published a paper in the Physical Review titled, "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" It became known instantly as the EPR paper. It wasn't designed to argue that quantum mechanics was producing incorrect numbers. Rather, it was structured as a logical proof that quantum mechanics was an incomplete theory, that it was missing vital underlying information about the world. The EPR argument is elegantly simple. Imagine a physical process that produces a pair of particles sent off in opposite directions. These particles are entangled, meaning their physical attributes are strictly linked. If you measure the spin of particle A along a vertical axis and find it pointing up, you instantly know with 100% certainty that measuring particle B along the same axis will yield down. Now let the two particles fly light years apart. Allow particle A to reach an observer on Earth, while particle B travels to an observer near Alpha Centauri. According to standard quantum theory, neither particle possesses a definite spin orientation while in flight. They exist in an indefinite superposition. But the moment the observer on Earth measures particle A and finds it spinning up, the wave function collapses globally, and particle B's spin instantly resolves to down. Einstein found this absurd. For particle B's spin to become fixed at the exact instant particle A is measured on Earth, an instantaneous signal or physical influence would have to cross light years of space, traveling infinitely faster than light. That would explicitly destroy the core principle of special relativity. Because special relativity had been validated by every available test, Einstein concluded that no signal could possibly be traveling between the particles. Therefore, particle B must have already possessed a definite down spin long before it reached Alpha Centauri, and particle A must have carried a definite up spin the entire time. Quantum mechanics simply failed to account for these pre-existing physical properties. The theory was incomplete. There were hidden variables, unmeasured physical parameters, that determined the outcome of measurements in advance. Niels Bohr drafted a prompt, dense, and remarkably subtle response later that same year. His main argument was that Einstein's entire premise rested on an unexamined assumption that two separated particles could be treated as independent physical entities, totally distinct from one another and from the laboratory apparatus measuring them. Bohr maintained that this assumption of separability was precisely what quantum mechanics rejected. In an entangled quantum system, you do not have two individual particles sitting at different coordinates. You have a single, indivisible quantum system described by a unified wave function. You cannot talk about the real physical state of particle B independently of particle A, nor independently of the specific experiment configured to measure them. The very concept of an independent element of reality that Einstein relied upon was a classical hangover that simply did not apply to quantum systems. The debate never reached a clean resolution during their lifetimes. Einstein passed away in 1955, remaining convinced to his final day that a deeper, deterministic theory incorporating hidden variables would eventually replace quantum mechanics and restore local realism. Bohr died in 1962, holding firm to his belief that Einstein's demand for local physical properties was fundamentally misguided. For nearly 30 years, their famous disagreement was relegated to the realm of philosophy. Most working physicists ignored it entirely, adopting a practical attitude: use the wave function, run the calculations, build the technology, and don't worry about what happens behind the curtain. It was considered a philosophical dead end because both views made the exact same numerical predictions for the experiment anyone knew how to run. Whether the particles carried hidden variables or belonged to an indivisible wave function, the observed outcomes in a standard experiment appeared completely identical. It took an unpretentious Northern Irish physicist working at CERN to realize that everyone had missed a staggering mathematical trick. John Stuart Bell was an accelerator designer at CERN. His daily responsibilities involved calculating magnetic fields and beam dynamics for high-energy particle colliders. But fundamental quantum mechanics was his personal obsession. In 1964, while on sabbatical, he published a paper in an obscure, short-lived journal called Physics Physique Physica. The paper was titled On the Einstein-Podolsky-Rosen Paradox. Bell did something extraordinary. He took what had been an endless philosophical argument about reality and transformed it into a clear, experimental, mathematical test. He posed a direct question. Suppose Einstein is right. Suppose particles carry hidden variables, definite, pre-existing physical properties that dictate their behavior, and suppose that no physical influence can travel faster than light. What absolute limit does that impose on how strongly the measurement results of two distant particles can correlate with one another? Bell worked through the calculus for measuring entangled particle spins across varying observational angles. He derived a mathematical formula now known as Bell's inequality. The core logic is astonishingly robust. If local realism holds true, if particles have real, objective properties before they are measured, and if local signals respect the speed of light, then the correlations between measurement outcomes taken at different angles must stay below a fixed numerical ceiling. There is an absolute upper limit to how coordinated those distant measurements can be. Bell then calculated what standard quantum mechanics predicts for those exact same measurement angles. The math was unambiguous. Quantum mechanics predicts correlation values that breach this ceiling. The implications were profound. If you construct an experiment that measures entangled particles at these specific relative angles, and the measured correlations exceed Bell's mathematical ceiling, then Einstein's local hidden variables are not just unlikely. They are mathematically impossible. Bell had created a definitive trial for the nature of existence. For the first time in history, you could build an apparatus in a basement lab and physically measure whether the universe was locally real. The first serious attempt to build and run a Bell test occurred in 1972 at UC Berkeley, carried out by John Clauser and graduate student Stuart Friedman. They built a complex machine that excited calcium atoms so they would emit pairs of entangled photons traveling in opposite directions toward polarizers. When they compiled the statistical correlations, the numbers violated Bell's inequality. The data matched the predictions of quantum mechanics, explicitly contradicting the limit required by local realism. Despite the monumental nature of this result, the broader physics community largely brushed it off. Foundations of quantum mechanics was viewed as a career dead-end hobby for eccentrics. Clauser faced substantial pushback for spending laboratory resources on what many considered a solved or irrelevant issue. Furthermore, early tests contained potential experimental loopholes that kept the debate alive. The first major objection was the detection loophole. Early instruments only registered a small fraction of the photon pairs emitted. A skeptic could argue that the detected photons were a biased sample, and that if every photon pair had been measured, the overall average would have obeyed local realism. The second major objection was the locality loophole. The orientation of the polarizers was set before the photons were emitted from the calcium source. A local hidden variable system could theoretically know the configuration of the polarizers in advance and adjust the particles' internal states before they were released. In the early 1980s, French physicist Alain Aspect set out to close the locality loophole at the Institut d'Optique in Orsay. Aspect constructed a dynamic experiment where the measurement angles of the polarizers were changed while the photons were actively in flight. The settings were switched randomly every few nanoseconds. The distance between the detectors was large enough that for a signal to travel from one polarizer to update the other in time to manipulate the outcome, that signal would have to travel significantly faster than the speed of light. Aspect's results were definitive. Even with high-speed switching in place, the correlations breached Bell's limit. The universe refused to obey local realism. Over the subsequent 3 decades, Anton Zeilinger pushed the boundaries of Bell tests to extreme scales. His group engineered entangled photon pairs inside fiber optic cables running beneath the Danube River, expanded test distances across the Canary Islands, and eventually bounced entangled photons off orbiting satellites. In 2015, multiple research teams across the globe, led by Ronald Hansen at Delft University alongside independent groups at NIST in Boulder and the University of Vienna, simultaneously conducted loophole-free Bell tests. They used high-efficiency detectors separated by wide physical distances, switching detector states via ultra-fast quantum random number generators. Every loophole was systematically shut down. The mathematical limit set by local realism was broken beyond all statistical doubt. When Aspect, Clauser, and Zeilinger jointly received the 2022 Nobel Prize in Physics, the scientific community acknowledged that 50 years of painstaking experimental refinement had settled the matter once and for all. Physical reality, at its deepest level, does not conform to local realism. When asked about the deeper philosophical meaning of these findings after his Nobel win, John Clauser famously admitted, "I'm still totally confused about what's going on." That wasn't false modesty. The experiments definitively dismantled Newton and Einstein's classical picture of the world, but they didn't leave a neat, intuitive replacement behind. It is critical to recognize what Bell's theorem actually proves. It is a no-go theorem. It doesn't spell out precisely what reality is. It dictates what reality cannot be. It mathematically proves that no physical theory combining both local influences and pre-existing objective properties can ever reproduce the observational facts of our world. You can preserve locality if you are willing to give up realism, accepting that physical properties don't exist until measured. You can preserve a form of realism if you are willing to accept non-locality, acknowledging that physical influences can act instantaneously across vast spatial distances. You can embrace many worlds theories or explore superdeterminism, but you cannot have both locality and realism simultaneously. The universe simply does not permit it. This brings us squarely to the central mystery that keeps Quantum Foundation's researchers up at night, the measurement problem. Schrödinger's equation is elegant, continuous, and fully deterministic. It describes how a physical system's wave function smoothly evolves over time. But the moment a measurement occurs, the math abruptly snaps. The continuous, multi-option wave function appears to instantaneously collapse down to a single, concrete outcome. The fundamental issue is that Schrödinger's equation itself contains zero mathematical mechanism for this collapse. The theory, as traditionally taught, relies on an artificial rule appended by hand. Use Schrödinger's smooth equation right up until an observation happens, then instantly throw out the wave function and pick a single value based on probability rules. In 1932, the mathematical genius John von Neumann formalized this strange dual structure. He pointed out that quantum mechanics relies on 2 totally contradictory processes. Process 2, the smooth, deterministic, continuous wave evolution dictated by Schrödinger's equation. Process 1, the sudden, random, non-unitary collapse that occurs during an act of measurement. The theory uses both, yet offers no scientific criteria for when Process 2 stops and Process 1 takes over. What constitutes a measurement? Does it require a human mind? Does it happen when a photon hits a physical sensor? When a digital circuit flips a bit? Von Neumann proved mathematically that you can push the boundary, the quantum cut, wherever you like without altering the final calculations. You can treat the particle as quantum the detector as quantum, the computer logging the data as quantum, and even the retina of the scientist reading the display as quantum. The equations never tell you where the quantum behavior ends and classical reality begins. Erwin Schrödinger constructed his notorious cat paradox to highlight this exact absurdity. Place a cat in a sealed steel chamber with a radioactive atom, a Geiger counter, a hammer, and a vial of cyanide. If the atom decays, the counter triggers the hammer, breaking the vial and killing the cat. If it doesn't decay, the cat lives. According to a literal reading of quantum mechanics, after 1 hour, the radioactive atom rests in a superposition of decayed and undecayed. Therefore, the Geiger counter is in a superposition of triggered and untriggered. Therefore, the cat is in a superposition of living and dead, simultaneously existing in a blurry linear combination of both states until an observer opens the container. Schrödinger considered this idea utterly preposterous. The cat is obviously alive or dead long before anyone lifts the lid. Yet the standard mathematical formalism provided no logical exit strategy. Modern physicists often appeal to a real physical mechanism known as quantum decoherence. When a quantum system interacts with its surrounding environment, colliding with stray air molecules, thermal photons, or structural atoms, its delicate phase relationships rapidly bleed out into the surrounding world. Decoherence happens blazingly fast for macroscopic objects. It effectively destroys the measurable interference patterns between different quantum possibilities, making a macroscopic system look and act as though it is purely classical. Decoherence explains with extreme precision why we never observe macroscopic objects in ghostly superpositions. But it does not solve the underlying measurement problem. Decoherence doesn't collapse the wave function. It simply entangles the primary system with billions of environmental particles, spreading the superposition out so broadly that it becomes practically impossible to detect. It tells us why the different possibilities stop interacting with one another, but it doesn't explain why we experience this specific reality rather than one of the other available options. This lingering conceptual void split quantum physics into competing interpretations, none of which offer a comfortable classical picture. The Copenhagen interpretation, championed by Bohr, simply declares the question out of bounds. It asserts that quantum mechanics is merely an abstract mathematical tool used to calculate the probability of specific observational outcomes. Asking what a system is doing when nobody is looking is considered a meaningless, non-scientific question. While practically useful, this framework leaves many feeling that physics has abandoned the goal of describing objective reality. The many worlds interpretation, introduced by Hugh Everett III in 1957, takes the mathematics dead seriously. It throws out process one entirely. There is no collapse. Schrödinger's equation applies universally at all times to everything. When a quantum system enters a superposition and interacts with a measuring device, the entire universe branches. In one reality, the spin was up and you observed it as up. In another parallel branch, the spin was down and an identical copy of you observed it as down. Every quantum event endlessly splits reality into countless diverging timelines. It restores absolute determinism to the universe, but at the cost of expanding reality into an unfathomable infinite multiverse. De Broglie-Bohm pilot wave theory takes a different route. It restores realism and determinism by proposing that particles are entirely real, localized objects that always possess precise spatial coordinates. However, their trajectories are guided through space by an explicit, physically real wave, the pilot wave. To make this work, the pilot wave must update instantaneously across the entire universe, making the theory directly non-locally connected across space. Each candidate theory asks us to pay a massive conceptual tax. Copenhagen asks us to surrender the existence of an objective reality. Many worlds asks us to accept an infinity of unobservable parallel universes. Pilot wave theory asks us to accept explicit, faster-than-light spatial connections everywhere at once. And this conceptual crisis hits an absolute wall when you attempt to push quantum mechanics to its ultimate limit, the universe as a whole. In standard quantum experiments, you always have a clear system inside a lab being observed by an external environment. But if you try to write down a quantum wave function for the entire cosmos, there is no outside. There is no external sensor, no ambient environment to induce decoherence, and no external observer to cause a collapse. This realization led physicists John Wheeler and Bryce DeWitt to formulate the Wheeler-DeWitt equation, a mathematical model meant to capture the quantum state of the entire universe. When you sit down and analyze the Wheeler-DeWitt equation, something extraordinary pops out. The time parameter entirely vanishes. The variable $t simply isn't there. The fundamental quantum equation governing the universe as a whole is totally static. It doesn't describe a system evolving through space and time. It describes a timeless, frozen state of interrelated quantum correlations. This leads directly to a radical conclusion that has been steadily gaining traction across theoretical physics. Time and space are not fundamental parameters woven into the fabric of reality. They are emergent phenomena. Just as the concepts of temperature or wetness do not exist for an individual, isolated water molecule, but emerge naturally when billions of molecules interact collectively, space and time may not exist at the deepest quantum level. They may simply be coarse, large-scale, low-resolution geometric descriptions arising from complex patterns of quantum entanglement. This brings us directly to the recent breakthroughs in quantum computing and holographic physics that have dominated science reporting. In late 2022, researchers using Google's Sycamore quantum processor announced they had configured a quantum circuit to simulate the mathematical dynamics of a traversable holographic wormhole, a bridge through spacetime known in general relativity as an Einstein-Rosen bridge. The media coverage was chaotic, with many outlets mistakenly implying that a literal physical portal had been ripped open inside a silicon microchip. That wasn't what happened. What actually occurred was far more interesting. The researchers programmed a network of qubits using a theoretical framework known as the ADES-CFT correspondence, discovered by physicist Juan Maldacena in 1997. ADES-CFT, anti-de Sitter conformal field theory, is a rigorous mathematical duality. It proves that a quantum system operating on a flat surface without gravity can be translated, point for point, into a higher dimensional gravitational universe filled with bent spacetime and black holes. The two descriptions are mathematically identical. They are two different languages expressing the exact same underlying physical reality. The researchers configured their qubits to represent a strongly interacting quantum system on the boundary. They inserted a unit of quantum information into one side of the qubit array, allowed it to instantly scramble across the entangled state, and then observed it reconstruct itself neatly on the opposite side of the array. Mathematically, in the higher dimensional dual picture, this process is entirely indistinguishable from a particle entering a traversable wormhole, passing through a spatial shortcut and popping out the other side. The processor didn't bend physical space inside the room. Instead, it proved that the complex dynamics of gravitational geometry, including spatial shortcuts like wormholes, can be precisely encoded within and generated by pure quantum entanglement. Space, geometry, and distance were acting as secondary surface-level reflections of fundamental quantum connectivity. This conceptual shift turns traditional physics completely upside down. For 300 years, we assumed that space was the primary container and that quantum particles were tiny items placed inside that container. Holographic duality suggests the exact opposite. Fundamental reality consists of abstract quantum information and entanglement networks, while space is merely the coarse dimensional image projected by those correlations. This brings us to the astonishing benchmark achieved by Google's Willow processor in late 2024. The Willow architecture, operating with 105 superconducting qubits, ran a standard computational benchmark known as random circuit sampling. The system executed a series of complex, highly entangled quantum operations and measured the resulting state. Willow completed the computational task in under 5 minutes. To calculate the exact same outcome using the world's most powerful classical supercomputers would require an estimated 10 septillion years. To grasp the absurdity of that metric, our universe is approximately 13.8 billion years old. 10 septillion years is roughly 1 quadrillion times the total amount of time that has elapsed since the Big Bang. Why can a tiny chip chilling inside a cryostat outrun every classical computer on Earth by such a ridiculous margin? If you view the world through a classical Newtonian lens, this speedup looks like magic. A classical computer must evaluate states step by step, manipulating physical bits that represent definite ones or zeros stored at specific physical locations in space. To track a system of 105 entangled quantum entities, a classical computer must store and update two $105 distinct complex numbers simultaneously, a data load that exceeds the total number of fundamental particles in the observable universe. A quantum processor doesn't achieve this performance by simply doing classical arithmetic faster. It succeeds because it operates directly in the raw, high-dimensional Hilbert space of nature itself. It bypasses the secondary low-resolution classical spatial surface entirely. It uses the non-local, non-real architecture of quantum mechanics to allow complex multipath interferences to resolve computational problems in real time. David Deutsch, one of the founding pioneers of quantum computation, famously argued that the raw processing power of quantum devices provides direct empirical proof for the reality of non-local or multi-branch quantum structures. Whether you interpret this through the lens of many worlds, emergent holographic spacetime, or non-local field theories, the ultimate conclusion remains identical. The physical reality we navigate daily is missing the vast majority of what is actually occurring. When you weave these three threads back together, a coherent picture begins to take shape. The death of local realism, verified by Nobel-winning Bell tests, proved that physical objects do not carry fixed, independent properties while sitting inside a strictly local spatial grid. Holographic physics demonstrated mathematically and experimentally that spatial geometry, including gravitational phenomena, can be generated out of pure patterns of quantum entanglement. Quantum computational supremacy demonstrated that operating directly within raw, high-dimensional quantum states allows an information processor to easily execute operations that would demand more time than the classical age of the universe to compute step by step through space. All three lines of evidence point toward the exact same foundational realization. Spacetime is not the fundamental floor of existence. It is an emergent phenomenon. Spacetime is a user interface. Think of a modern computer screen. When you drag a folder across your desktop display, you see a square icon gliding across a two-dimensional grid. If you open up the monitor casing, you won't find tiny physical folders sliding across a glass plate. You will find silicon logic gates, voltage fluctuations, electromagnetic signals, and abstract binary sequences. The desktop interface isn't a lie. It is a functional, low-resolution simplification designed to let a user interact with complex underlying information without needing to compute millions of individual electron movements in real time. Physical space, localized coordinates, and the linear flow of time appear to function as nature's user interface. Newton's mechanics, special relativity, and classical logic operate brilliantly at the level of that interface. They allow us to build engines, land on moons, and throw baseballs. But when we push our experiments to extreme scales, cool system down to millikelvin, measure entangled photons over kilometer tracks, or run high-qubit processing chips, the interface breaks down. We catch glimpses of the raw, non-spatial code running underneath the display. We are not living inside a science fiction matrix simulation constructed by an alien programmer. The true takeaway is far more profound. Reality simply isn't constructed out of tiny, localized physical billiard balls bouncing off one another inside a grand, pre-existing spatial box. Space and time are not the backdrop of reality. They are the downstream products of a deeply interconnected, non-local quantum structure. The comfortable classical picture of reality built over 3 centuries didn't fail because it was useless. It failed because it was only the surface level of the story. Beneath the familiar world of fixed coordinates, solid objects, and ticking clocks lies an interconnected web of quantum state relationships that doesn't care about distance, doesn't wait for observers, and refuses to sit neatly inside the box of local space. The ultimate lesson of modern quantum mechanics isn't that the universe is fake or that science has lost its way. It is that the cosmos is vastly larger, deep, and write an equation for. Objective collapse models add tiny, nonlinear, random terms to the Schrödinger equation, effectively guessing at new laws of physics that have yet to be confirmed by any laboratory. Pilot wave theories add hidden particle positions guided by non-local potential fields that sweep across the cosmos faster than light. Everett looked at all of this clutter and asked a radical question. What if we just don't add anything? What if the Schrödinger equation isn't just an approximation that works until a human enters the room, but the total absolute truth about the universe? If you accept that simple premise, you are forced to accept its logical consequence. When a quantum system enters a superposition of two states, say an electron being both spin up and spin down, and that system interacts with a measuring device, the measuring device doesn't destroy the superposition. The measuring device enters a superposition too. It becomes a system that has recorded up entangled with an electron that is up, combined with a system that has recorded down entangled with an electron that is down. When a scientist looks at the reading on the display, the scientist's brain enters the superposition. There is now a state describing a scientist who saw up and a state describing a scientist who saw down. The two states, once entangled with their macroscopic environments, undergo rapid, irreversible decoherence. The mathematical terms that would allow them to interact or interfere with one another drop to effectively zero within fractions of a nanosecond. They become completely blind to each other. To the scientist inside the up branch, it feels as though the wave function abruptly collapsed, that a single random outcome occurred, and that the down possibility simply vanished into thin air. But the down branch didn't vanish. It is sitting right there in the global wave function of the universe, evolving according to the exact same Schrödinger equation, containing its own copy of the laboratory, its own copy of the scientist, and its own identical history up to the moment of measurement. This is the price of determinism. Everett returns to physics a fully deterministic universe, one where no random dice are rolled, no magic collapse occurs, and no mysterious boundary separates the quantum from the classical. But the tax he levies on our intuition is staggering. Reality is no longer a single timeline running through space. It is a Hilbert space of staggering dimensions, branching endlessly, containing an incomprehensibly vast ensemble of coexisting worlds. Yet, despite its sci-fi reputation, many modern theoretical physicists favor Everett's picture precisely because it is conservative. It doesn't modify the mathematics of quantum mechanics by a single character. It simply demands that we take the math literally. When you look closely at how these branches split, however, a fascinating geometric pattern emerges. The branching isn't occurring in physical space. You cannot point your telescope toward the sky and look in the direction of another branch. The splitting occurs in Hilbert space, the abstract, high-dimensional mathematical space where quantum wave functions live. In Hilbert space, distance isn't measured in meters or light years, but in degrees of orthogonality between wave functions. Two branches that have decohered are orthogonal to one another. The inner product of their mathematical states is zero. This means they occupy completely separate directions in Hilbert space. This brings us back to the central question that keeps haunting modern physics. If the fundamental state of the universe is just a single giant wave function evolving smoothly in Hilbert space, where did physical space come from in the first place? How do you get three spatial dimensions, light years of distance, and the force of gravity out of abstract mathematical vectors pointing in an infinite dimensional Hilbert space? To answer that, theoretical physicists in the late 2010s and early 2020s began reversing the standard question. For a century, physicists started with space, put particles inside it, and derived their quantum state. Modern theorists are trying to do the exact opposite. Start with pure quantum state relationships in Hilbert space and see if physical space naturally precipitates out of them. Part 7. Building space from pure entanglement. Imagine you are given a massive heap of abstract data points. There are no coordinates attached to them, no north or south, no left or right, no concept of distance. All you are given is a matrix that tells you how strongly correlated each point is with every other point. Point A has a strong quantum entanglement with point B. Point A has a very weak entanglement with point C. Point B has zero entanglement with point D. If you are a topologist, you can use those correlation strengths to define a notion of distance. You can define 2 points as being close together if they share a massive amount of mutual quantum entanglement. You can define 2 points as being far apart if their entanglement is negligible. If you take this mathematical trick seriously, a breathtaking possibility opens up. What if distance in our physical world isn't an absolute property of space, but a measure of quantum entanglement? What if two objects are close to each other in your living room simply because their underlying quantum degrees of freedom are strongly entangled? And what if two galaxies are separated by billions of light years because their underlying quantum components share virtually no entanglement at all? This isn't a vague metaphor. It is a precise mathematical program known as emergent gravity, pioneered by theoretical physicists like Mark van Ramsdonk, Eric Verlinde, and Sean Carroll. In 2010, Mark van Ramsdonk published a seminal essay that changed how theoretical physicists view the fabric of the universe. He used the mathematical machinery of the ESCFT correspondence to demonstrate what happens to a smooth geometric spacetime when you gradually reduce the quantum entanglement between its underlying components. In the holographic framework, a smooth, connected, higher-dimensional gravitational spacetime, the bulk, is mathematically equivalent to quantum field theory operating on a lower-dimensional boundary. Van Ramsdonk showed that the smooth connectivity of the bulk spacetime depends directly on the entanglement between different regions of the boundary quantum theory. If you take the boundary quantum state and artificially dial down the entanglement between its left half and its right half, something dramatic happens to the spacetime geometry inside the bulk. The physical space inside the bulk begins to pinch off. The spatial bridge connecting the left region to the right region narrows, warps, and stretches. If you completely sever the quantum entanglement between the two halves of the boundary theory, the spatial geometry inside the bulk literally tears apart. The universe snaps into two disconnected, isolated bubbles of space. Space itself, Van Ramsdonk showed, is the physical glue held together by quantum entanglement. Remove the entanglement and the spatial continuum dissolves. Space is not the background container in which quantum entanglement happens. Quantum entanglement is the mortar out of which space is built. This realization offered a fresh perspective on one of the oldest, most intractable paradoxes in theoretical physics, the black hole information loss paradox. Part 8, black holes, firewalls, and the ultimate test of locality. In the mid-1970s, Stephen Hawking made a discovery that sent shockwaves through physics. Using quantum field theory in curved spacetime, he demonstrated that black holes are not completely black. They emit subtle thermal radiation, now called Hawking radiation, and gradually lose mass over time. Given enough time, a black hole will radiate away all of its energy and evaporate completely into a cloud of featureless heat. This created a catastrophic contradiction at the heart of science. In quantum mechanics, there is a fundamental rule called unitarity. Unitarity dictates that information can never be truly destroyed. If you know the complete quantum state of a closed system today, you can, in principle, use Schrödinger's equation to calculate its exact past and its exact future. The total probability of all possible outcomes must always add up to 100%. Information may become scrambled, messy, and practically unrecoverable, like burning encyclopedia and scattering the ashes, but it is never erased from the universe. Hawking's calculation implied that if you drop an encyclopedia into a black hole and wait for the black hole to completely evaporate, the outgoing Hawking radiation is purely random, thermal noise. The information that fell into the black hole appears to be completely erased from existence. If Hawking was right, quantum mechanics was wrong. Unitarity failed, and fundamental probability wasn't preserved. If Hawking was wrong, then general relativity, which dictates that nothing, not even information, can escape from inside a black hole's event horizon, had to break down at the horizon in ways no one could explain. For nearly 4 decades, the black hole information paradox remained an open wound in fundamental theory. Then, in 2012, 4 physicists, Ahmed Almhiri, Donald Merolf, Joseph Polchinski, and James Sully, collectively known as AMPS, pushed the paradox to an alarming extreme. They realized that for outgoing Hawking radiation to carry information out of an evaporating black hole, preserving unitarity, each newly emitted photon must be quantum entangled with all the radiation that was emitted previously. However, standard general relativity demands that any particle crossing the event horizon must be smoothly entangled with its partner particle falling inside the black hole. Quantum mechanics has a strict mathematical rule known as the monogamy of entanglement. A quantum system cannot be simultaneously maximally entangled with two independent systems at the same time. A particle cannot be fully entangled with its twin falling into the black hole and fully entangled with the early Hawking radiation sitting light years away outside the black hole. To break this illegal monogamy, the quantum entanglement across the event horizon must be violently severed. Severing quantum entanglement releases a massive amount of energy. AMPS calculated that this energy would form a blinding, hyperdense wall of pure fire right at the event horizon. A firewall. If the firewall hypothesis was correct, an astronaut floating casually toward a supermassive black hole wouldn't sail smoothly across the event horizon as Einstein's general relativity predicted. The moment they reached the boundary, they would slam into an infinitely dense wall of high-energy particles and be instantly incinerated. General relativity insisted the horizon was smooth and unremarkable. Quantum mechanics, pushed to its logical conclusion, insisted the horizon was a destructive firewall. Theoretical physics had hit a wall of its own. The breakthrough came from an unexpected direction, led by Juan Maldacena and Leonard Susskind in 2013. They proposed a radical, startlingly simple identity that bridges quantum information and general relativity, ER equals EPR dolls. Part 9, ER equals EPR and the wormhole on a chip. The acronym $E stands for Einstein-Rosen bridge, a theoretical shortcut through spacetime predicted by general relativity in 1935, commonly known as a wormhole. The acronym EPR stands for Einstein-Podolsky-Rosen, the famous 1935 paper that defined quantum entanglement. For nearly 80 years, physicists viewed Einstein's 1935 wormhole paper and his 1935 quantum entanglement paper as two completely unrelated contributions to science. One was a geometric curiosity in classical gravity. The other was a foundational critique of quantum mechanics. Maldacena and Susskind argued that they were not two different phenomena at all. They were two different descriptions of the exact same physical reality. ER equals EPR asserts that whenever two quantum particles become entangled, they are connected by a microscopic quantum mechanical wormhole. If you entangle two electrons on Earth and separate them across the galaxy, they are not communicating through spooky, faster-than-light signals crossing physical space. They are directly connected by a tiny spatial bridge through the bulk geometry, a wormhole so small that no macroscopic signal can pass through it, but strong enough to maintain their quantum correlation. If you take a massive collection of entangled particles, crush them into two separate black holes, and keep the two black holes maximally entangled with each other, those two black holes will be connected through the interior by a smooth, traversable macroscopic Einstein-Rosen bridge. The interior of the black hole, the very space that seemed to trap information forever, is physically continuous with the distant region of space occupied by the entangled radiation on the outside. Information isn't escaping by breaking the speed of light or leaking out through a tear in space. It is traveling smoothly through the internal wormhole bridge provided by EP entanglement. This brings us straight back to the experiment that made headlines worldwide, the holographic wormhole simulated on Google's quantum processor. When physicists at Caltech, Harvard, and Google mapped a simplified model of this holographic protocol onto a quantum circuit, they weren't pretending. They configured a system of physical qubits so that their entanglement dynamics precisely mirrored the SYK, Sakhtev-Ye-Kitev model, a quantum field theory known to be mathematically dual to a two-dimensional gravitational universe containing a traversable wormhole. They injected a qubit of information into one side of the chip. The quantum state instantly scrambled across the complex, entangled network of surrounding qubits, appearing to be totally randomized and destroyed. But moments later, as the phase relationships evolved according to the holographic protocol, the information cleanly unscrambled itself and reemerged intact on the far side of the chip. In the boundary description, the chip itself, what occurred was complex quantum state manipulation, decoherence, and rapid information scrambling across an entangled network. In the bulk description, the dual gravitational universe, what occurred was a particle dropping into a black hole, traversing a wormhole bridge, and emerging safely out of a connected white hole on the other side. The experiment didn't bend space inside the physical room where the cryostat was sitting. What it proved was far more fundamental. It demonstrated that the complex dynamics of gravitational geometry are real, testable features of non-local quantum state entanglement. Geometry is not an independent background, it is an emergent property of quantum information processing. Part 10, the computational universe and the speed of Willow. If spacetime is an emergent projection constructed out of underlying quantum entanglement, then the universe at its deepest level is not a mechanical clock, nor a fluid field, nor a spatial stage. It is an information processor. This helps clarify why processors like Google's Willow achieve computational benchmarks that seem physically absurd under classical terms. When Willow executed its random circuit benchmark in under 5 minutes, a task requiring an estimated 10 septillion years for a conventional classical supercomputer, it highlighted the massive computational bottleneck imposed by classical space and time. A classical supercomputer operates entirely within the surface interface. It must assign binary states to distinct physical locations, flip a transistor here, send a pulse down a wire there, store a bit in a specific capacitor. To evaluate a problem involving hundreds of entangled variables, a classical machine is forced to explicitly compute every single branch, every single coordinate, and every single linear operation one by one, battling against the spatial limits of light propagation and thermal dissipation. A quantum processor doesn't work by packing more classical operations into a smaller physical space. It works by stepping off the spatial stage entirely. By entangling 105 qubits, Willow creates a unified quantum state that lives directly inside a 105-dimensional complex Hilbert space. The computation doesn't take place by sliding physical signals across a two-dimensional silicon board. It takes place through the high-dimensional interference of quantum phase states. The processor allows millions of computational paths to interfere constructively and destructively simultaneously, letting the underlying quantum state settle into the answer naturally. The reason classical computers take 10 septillion years to simulate this process is that trying to map high-dimensional quantum entanglement back onto a linear, three-dimensional spatial grid is brutally inefficient. It is like trying to draw a millimeter by millimeter two-dimensional map of an entire 11-dimensional hypercube. The computational overhead explodes exponentially. The quantum chip isn't performing magic. It is simply operating in the natural language of fundamental reality, while our classical computers are stuck translating everything into the clunky, low-resolution dialect of localized spacetime. Part 11, the honest boundary of what we actually know. It is easy, when looking at these breakthroughs, to let enthusiasm run away with the narrative. It is easy to declare that space is an illusion, that time doesn't exist, or that we live inside a holographic computer. That is where popular science often crosses the line into sensationalism. So let us step back and establish the clear, honest boundaries of where theoretical physics genuinely stands today. First, emergent spacetime and holographic duality are not yet a fully unified, complete theory of nature. The ADS-CFT correspondence operates cleanly in universes with a negative cosmological constant, universes that are shaped like anti-de Sitter space with a cold saddle-like spatial curvature. Our actual observable universe appears to have a tiny positive cosmological constant. It is an accelerating, expanding de Sitter space. Translating the rigorous mathematics of holographic duality from anti-de Sitter space to our real-world de Sitter universe is one of the most difficult, unresolved challenges in theoretical physics today. The dual boundary theory for an expanding de Sitter universe remains elusive, and theoretical physicists are actively arguing over how, or even if, the holographic principle applies to our cosmic horizon. Second, closing the loopholes in Bell's inequality proves that local realism is dead, but it does not tell us which interpretation of quantum mechanics is correct. The experimental data from Aspect, Zeilinger, and Hansen cannot distinguish between Everett's many worlds, de Broglie-Bohm's non-local pilot waves, or cubism, quantum Bayesianism. Every single one of these interpretations yields identical numerical predictions for every experiment we can perform today. Choosing between them remains, for now, a matter of theoretical elegance, mathematical preference, and philosophical risk tolerance. Third, Simulating the dynamics of a holographic wormhole on a 9-qubit or 105-qubit quantum chip is a profound demonstration of quantum duality, but it is not the same thing as creating a gravitational singularity in a laboratory. The qubits on the silicon chip are made of aluminum or transmon circuits, obeying standard electromagnetic laws in our laboratory's spacetime. The wormhole exists in the mathematical dual space encoded by those qubits, not as a physical tear in the air inside the room. Acknowledging these limitations doesn't diminish the story. If anything, it makes the real story far more compelling. We do not need to invent hyperbolic sci-fi tropes to make modern physics exciting. The sober, verified, laboratory-tested reality is already wild enough. We know, beyond all experimental doubt, that the physical properties of objects do not exist as fixed, independent attributes prior to measurement within a local spatial grid. We know, through rigorous mathematics, that gravitational fields and spatial dimensions can be fully mapped onto non-gravitational quantum systems operating in lower dimensions. We know, through direct hardware tests, that quantum information systems can navigate computational state spaces so immense that no classical machine bound by spatial limits could ever map them in the lifespan of the cosmos. Part 12, the view from the edge of the stage. For 300 years, humanity leaned on a comfortable, intuitive picture of the cosmos. Isaac Newton gave us a cosmic stage built of absolute space and absolute time, filled with tiny, solid billiard balls bouncing off one another according to precise mechanical laws. It was a universe that made sense to our senses. It was a universe where things stayed put when we looked away, where causes traveled neatly from point A to point B, and where space was the eternal, unyielding container holding everything together. Einstein bent that stage, warped it, and made it dynamic, showing that time and space could stretch, flex, and ripple under the influence of mass and energy. But he fought with every ounce of his intellect to keep the stage local, real, and independent of observation. He needed the physical world to be separable, objective, and anchored to specific coordinates in spacetime. The experiments of the last 50 years, from John Clauser's early calcium lasers in Berkeley to Alain Aspect's high-speed switches in Orsay, from Anton Zeilinger's fiber networks beneath the Danube to Ronald Hansen's loophole-free diamond centers in Delft, and straight through to modern holographic simulations running on superconducting quantum chips, have systematically dismantled that classical stage. The stage is not the bottom floor of reality. Space and time are not the fundamental bedrock upon which the universe is constructed. They are the surface ripple, the coarse temperature, the macroscopic desktop display. Beneath the stage lies a vast, non-local network of quantum states, entangled information, and high-dimensional Hilbert spaces. Distance is not an absolute barrier. It is a measure of quantum correlation. Time is not a relentless, ticking universal clock. It is an emergent relationship between entangled states evolving within a timeless global wave function. We are not standing at the end of physics. We are standing at the absolute beginning of a completely new conceptual era. We are just beginning to learn how to write equations that don't assume space as a starting condition. We're just beginning to build processors that operate directly in the raw, non-local language of quantum states, rather than the translated dialect of classical bits. We are finally learning to look past the user interface and catch a glimpse of the fundamental engine running underneath. The universe is not locally real. It is strange, it is non-local, and it is far more deeply interconnected than our everyday senses were ever designed to perceive. And as our tools get sharper, our quantum processors grow more powerful, and our theoretical frameworks push deeper past the boundary of space-time, the picture that emerges is not one of chaos or illusion, but of a reality far more unified, elegant, and breathtaking than anything Isaac Newton could have possibly imagined. Part 13, the thermodynamics of reality and the arrow of time. If space is an emergent projection built out of quantum entanglement, what does that mean for time? In our everyday lives, nothing feels more real, more inexorable, or more brutal than time. Coffee cools down. It never spontaneously boils. Glass shatters. It never gathers its shards off the floor to rebuild itself into a pristine vase. We remember the past, but we are completely blind to the future. This one-way street is what Arthur Eddington famously christened the arrow of time. For centuries, classical physics located the origin of this arrow in the second law of thermodynamics. The second law states that the total entropy, the degree of microscopic disorder or chaos, of an isolated system must always increase over time. The universe, we were told, began in a state of extraordinarily low entropy at the Big Bang and has been winding down ever since, coasting toward an inevitable, featureless heat death, where all energy gradients flatten out and nothing interesting can ever happen again. Yet, if you inspect the fundamental equations of classical mechanics, special relativity, or even standard quantum wave mechanics, you encounter an unsettling paradox. The microscopic laws of physics are entirely time reversible. If you record a video of two ideal billiard balls colliding on a table and play it in reverse, you cannot tell which direction the film is running. The math works identically in both temporal directions. The same holds true for Newton's laws of gravitation, Maxwell's equations of electromagnetism, and Schrödinger's equation for an isolated quantum system. If you replace the time variable t-dal with nias t-dal, the equations still hold. So where does the irreversible one-way arrow of time come from if the underlying fundamental laws don't care whether time runs forward or backward? The traditional answer was statistical. There are simply vastly more ways for a system to be disordered than to be ordered. If you scramble a Rubik's Cube at random, you are statistically guaranteed to end up with a chaotic mess rather than neatly solved monochromatic faces, simply because the number of disordered configurations vastly outnumbers the ordered ones. The arrow of time, in this classical view, was not a fundamental property of matter, but a statistical artifact of large numbers. However, once you remove spacetime as the fundamental bedrock of physical reality, the thermodynamic explanation reveals a much deeper, purely quantum origin. Time's arrow is not driven by classical particles bouncing around and getting messy. It is driven by the relentless, irreversible spread of quantum entanglement. Consider an isolated quantum system, say a hot gas confined a perfectly sealed, perfectly insulated container. At the initial moment, let us assume the gas molecules are in a pure, unentangled quantum state. Every molecule's wave function is distinct and localized. As time progresses, the molecules collide. Each collision causes the quantum states of the colliding particles to become entangled with one another. As trillions of collisions occur every microsecond, the quantum entanglement doesn't remain confined to pairs of particles. It cascades. Particle A entangles with particle B, which then entangles with particle C, which entangles with particle D. Very quickly, the local physical properties of any individual particle become entirely smeared out across the entire collective wave function of the gas. If you bring a detector to measure a single gas molecule late in the process, that single molecule will look utterly thermal, random, and maximum entropy. Why? Because the information that originally defined its individual state has been completely distributed into complex, non-local entanglement correlations shared across billions of surrounding particles. This process is called thermalization through quantum entanglement, or the eigenstate thermalization hypothesis, ETH. The arrow of time, at its deepest level, is simply the direction in which quantum information becomes increasingly non-local. Past corresponds to a state where quantum information is localized and accessible in small, individual systems. Future corresponds to a state where that same information has bled out into complex, multi-particle entanglement networks spanning the entire environment. You cannot reverse the shattered vase because, to do so, you would need to precisely gather every scrap of non-local quantum entanglement that bled out into the floorboards, the surrounding air molecules, and the ambient thermal photons, and force them all to unentangle simultaneously. The math permits it, but the non-local distribution of information renders it practically impossible. This insight fundamentally changes how we view time. Time is not an invisible, majestic river flowing steadily through the cosmos. Time is the measure of quantum state information scrambling across Hilbert space. This leads directly to a startling cosmological question. What happens when you try to trace this process all the way back to the very beginning? Part 14. The Big Bang without a singular space. For a century, standard Big Bang cosmology presented humanity with a terrifying, mind-bending image. Roughly 13.8 billion years ago, The entire observable universe, every star, galaxy, planet, and light beam, was compressed into an infinitely small, infinitely dense, infinitely hot point called a gravitational singularity. At this singularity, space and time themselves were born, and before it, the concept of before was rendered meaningless. Physicists always hated the singularity. In physics, when your mathematical equations return an infinity, it doesn't mean nature has done something miraculous. It means your theory has broken down and stopped making sense. A gravitational singularity was simply general relativity's dramatic way of admitting, I don't know what happens here. The reason general relativity fails at the Big Bang is that it treats space as a continuous, smooth fabric. As you compress space down to scales smaller than the Planck length, about 1.6 times 10 to the minus 35 meters, the smooth continuum assumption completely collapses. You cannot use a fluid equation to describe an individual atom, and you cannot use smooth general relativity to describe the ultramicroscopic quantum realm. When you re-examine the origin of the universe through the lens of emergent spacetime and holographic quantum information, the singular point at the beginning of time completely disappears. If space is an emergent structure woven from quantum entanglement, then compressing the universe does not mean squeezing physical matter into a tiny spatial dot inside a pre-existing void. It means examining a quantum state where the total amount of spatial entanglement approaches zero, or where the holographic boundary degrees of freedom are packed in an ultra-dense, highly entangled matrix. In this picture, the Big Bang was not an explosion in space, nor was it the violent creation of space out of absolute nothingness. The Big Bang was a phase transition, a cosmic event akin to steam condensing into liquid water. Before the phase transition, the universe existed in a purely quantum, non-spatial phase. There were no light years, no spatial dimensions, no geometry, and no ticking clocks. There was only a vast, highly connected quantum state evolving in Hilbert space. As this quantum state underwent a specific structural change, patterns of entanglement began to settle into a stable, low-energy configuration that could be macroscopically mapped as a smooth, expanding three-dimensional spatial geometry. What we call the Big Bang was simply the moment our macroscopic user interface turned on. It was the instant where quantum correlations organized themselves into a format that looks to macroscopic observers like us like an expanding bubble of hot space and time. Asking what happened before the Big Bang in a spatial sense is like asking what is the temperature of a single isolated electron. The question applies a macroscopic emergent concept to an underlying regime where that concept simply does not exist. This phase transition view of the early universe solves several massive cosmological puzzles that plagued classical Big Bang theory for decades. Take, for example, the horizon problem. When we point microwave telescopes at opposite sides of the night sky, measuring the cosmic microwave background, CMB, the lingering thermal afterglow of the early universe, we find that the temperature is astonishingly uniform. It is the same to within 1 part in 100,000, no matter which direction in the sky we look. Under standard relativity, two regions on opposite sides of the visible universe are separated by such immense spatial distances that light could never have traveled between them in the time available since the Big Bang. They were never in causal contact. So how could they possibly know to be at the exact same temperature? Standard cosmology invoked a rapid exponential expansion called cosmic inflation to explain this, proposing that a microscopic patch of space was stretched by an absurd factor in a fraction of a second, smoothing out all variations. Emergent quantum spacetime offers an even more direct explanation. Those distant regions of the sky are at the same temperature because, in the fundamental pre-spatial quantum state, they were not far apart at all. They were strongly entangled parts of a single unified quantum state. Their thermal equilibrium wasn't established by heat moving across physical space over time. It was built into the non-local entanglement structure from which space subsequently emerged. Space didn't bring things together. Non-local quantum correlations held them together before space even existed. Part 15, Cubism, the participant and the nature of physical law. If space, time, geometry, and causality are all emergent surface phenomena, where does that leave us? Where does the observer fit into a universe where reality isn't real until measured and space isn't space until entangled. This brings us to one of the most radical yet rigorous modern frameworks in quantum foundations, quantum Bayesianism, or cubism, pioneered by physicists Christopher Fuchs, Rudiger Schack, and N. David Mermin. Cubism takes its name from Thomas Bayes, the 18th century mathematician who formulated the probability rules for updating beliefs in the light of new evidence. For nearly a century, physicists debated what the quantum wave function actually represents. Is it a real physical wave undulating through space like an ocean wave, as pilot wave theory suggests? Is it an objective physical field containing parallel realities, as many worlds suggests? Cubism offers a daring alternative. The wave function does not exist in the physical world at all. The wave function is not a physical object, a field, or a cloud of matter. It is a mathematical bookkeeping tool used by an agent to quantify their own personal degrees of belief about the outcomes of future physical experiences. When a scientist measures an electron's spin and says the wave function collapsed from a superposition down to spin up, Cubism asserts that no physical wave collapsed across space. What actually happened was that an agent performed an action on the world, experienced a specific sensory outcomes, and instantly updated their internal probabilistic expectations about what will happen next. This sounds at first read like pure solipsism or subjective idealism, a philosophical retreat claiming that reality is all in your head. But Cubism is explicitly not solipsism. Cubism insists that the physical world outside our heads is overwhelmingly real. However, that external world does not consist of a prepackaged, fully formed classical reality waiting passively to be mapped. The universe is fundamentally open, unfinished, and participatory. When an observer performs a quantum measurement, they are not passively reading off an objective piece of pre-existing data like a clerk checking an inventory list. The act of measurement is an active, creative physical intervention. The observer pushes against the universe pushes back, and a brand new, unique physical outcome is created right at the point of interaction. John Archibald Wheeler, one of the greatest theoretical physicists of the 20th century, the man who coined the terms black hole, wormhole, and it from bit, called this the participatory universe. Wheeler argued that we must replace the old classical image of the scientist standing behind a thick sheet of protective glass, passively observing a clockwork nature ticking away inside. Quantum mechanics, Wheeler insisted, forces us to smash the glass. The scientist must reach in, install an apparatus, and choose which complementary question to ask. If you configure your apparatus to measure a wave, nature answers as a wave. If you configure your apparatus to measure a particle, nature answers as a particle. Nature does not possess an intrinsic wave or particle identity prior to that interaction. The outcome is born out of the collision between the agent and the cosmos. As Wheeler famously wrote, nothing is more important about the quantum principle than this, that it destroys the concept of the world as sitting out there, with the observer safely separated from it by a 20-centimeter slab of plate glass. Even to observe a localized electron, the experimenter must shatter the glass. He must reach in. The outcome depends on his choice. The universe is a participatory universe. If you combine Wheeler's participatory insight with the framework of emergent spacetime, the philosophical picture becomes strikingly clear. Physical laws, the equations of general relativity, the speed of light limit, the inverse square law of gravity, the rules of thermodynamics are not timeless commandments etched into the golden bedrock of absolute space. They are the statistical regularities that emerge when billions upon billions of individual quantum interactions take place collectively. They are the thermodynamics of quantum information. Just as the law that dictates that gas pressure doubles when you have a container's volume is not a fundamental law governing individual atoms, but a statistical emergent outcome of trillions of random molecular collisions, the geometric laws governing spacetime are the statistical emergent outcomes of countless quantum participatory events. Reality is not a static building. It is an ongoing dynamic computation. Part 16, The Practical Revolution, Why This Changes Everything. Up to this point, it is easy to view this entire narrative as a high-minded, esoteric exercise for theoretical physicists in chalk-dusted university offices. It is easy to assume that whether space is fundamental or emergent makes zero difference to daily human life. That assumption is completely wrong. Every single major technological revolution in human history occurred because humanity successfully peeled back one layer of reality's user interface and learned to manipulate the deeper mechanics running underneath. When our ancestors mastered thermodynamics, the macroscopic physics of fire, steam, and pressure, we built the engines that drove the Industrial Revolution. We transformed human society, even though we didn't yet understand atoms or subatomic particles. When 20th century physicists peeled back the thermodynamic layer and uncovered classical electromagnetism and quantum mechanics, we learned to manipulate the behavior of individual electrons moving through crystalline lattices. That understanding directly gave birth to the semiconductor, the transistor, the microchip, the laser, digital telecommunications, and the global internet. Every smartphone, GPS navigation signal, and medical MRI scanner operating on Earth today relies entirely on the first wave quantum mechanics developed by Planck, Einstein, Bohr, and Schrödinger. Now, in the 2020s, humanity is standing directly on the threshold of the second quantum revolution. We are no longer merely using quantum mechanics to explain the behavior of bulk materials like silicon or gas lasers. We are directly manipulating individual, entangled quantum states across complex circuits. We are engineering non-locality. Look at what is being actively constructed in research laboratories around the globe right now. First, quantum computing is transitioning from a theoretical demonstration into a disruptive industrial reality. When devices like Google's Willow processor execute benchmarks in minutes that would require classical supercomputers billions of years to process, they are not just breaking speed records. They are providing industry with a tool capable of simulating complex molecular chemistry with absolute precision. Classical supercomputers struggle to model simple molecules because tracking the quantum state of overlapping electron orbitals requires an impossible amount of classical memory. A high-qubit quantum processor operating directly in Hilbert space can simulate molecular dynamics natively. This means that over the next few decades, quantum hardware will allow chemists, material scientists, and pharmacologists to design room-temperature superconductors, hyper-efficient solar cells, ultra-dense battery chemistry, and targeted molecular therapies directly on a screen without years of wasteful trial-and-error laboratory synthesis. We will engineer materials atom by controlling their underlying quantum entanglement patterns. Second, quantum communication and the quantum internet are leaving the lab and entering orbital space. Researchers in China, Europe, and the United States have already deployed satellite networks capable of distributing entangled photon pairs over thousands of kilometers. These networks don't just offer unhackable encryption via quantum key distribution, QKD, where any attempt by an eavesdropper to measure the signal instantly collapses the entanglement and reveals the intrusion. They lay the physical foundation for a global interconnected quantum network where quantum processors can exchange pure entanglement directly. A global quantum internet won't send classical emails faster. It will allow geographically separated quantum processors to link their qubit arrays into a single, massive, non-local superprocessor that operates across planetary distances. Third, quantum sensing is reaching levels of precision that defy classical limits. By utilizing squeezed quantum states and entangled atomic lattices, modern atomic clocks can keep time so precisely that they will not lose or gain a single second over the entire age of the universe. These ultra-precise quantum sensors are not just fancy wristwatches. Because general relativity dictates that gravity slows down time, an atomic clock can detect an elevation change of a single millimeter simply by measuring the subtle change in the rate at which its atomic phase ticks. Quantum sensors are turning into ultra-high-resolution gravitational cameras. They will allow geophysicists to map subterranean water tables, track magma movements inside active volcanoes, locate deep underground mineral deposits, and scan human body tissue without firing a single particle of ionizing radiation, simply by measuring tiny variations in local emergent spacetime geometry. We are learning to control the interface by interacting directly with the non-local code running underneath it. Part 17, the human place in a non-local cosmos. There's a deep, instinctual fear that often surfaces when people first digest what modern quantum physics is telling us. When you tell someone that space isn't real, that time is emergent, that physical objects don't have definite properties when nobody is looking, and that their daily life unfolds on a low-resolution user interface projected out of abstract Hilbert space, the natural reaction is a feeling of cold, existential vertigo. It feels as though science is stripping away everything solid, everything familiar, and everything meaningful, leaving us floating in an alien, mathematical void of probability clouds and branching wave functions. It feels like the ultimate scientific displacement. When Copernicus proved that Earth was not the fixed center of the universe, but merely a rocky ball orbiting an average star, humanity felt displaced. When Darwin proved that humans were not created separately from nature, but evolved through natural selection alongside every other animal, humanity felt displaced. And when quantum mechanics proved that physical spacetime is not the fundamental floor of existence, it felt like the final absolute displacement. We aren't even sitting in a fundamental container. But if you look closely at what the physics actually dictates, that existential vertigo turns out to be based on a complete misunderstanding of the narrative. The classical Newtonian universe, the cold mechanical clockwork of rigid particles bouncing around in absolute indifferent space, was the truly terrifying picture. In Newton's universe, humanity was a completely passive accident. We were tiny, fragile piles of organic matter clinging to a rock, watching a cold, deterministic cosmos tick along like a massive steel machine that didn't know we were here, couldn't feel our presence, and would keep grinding along long after our extinction. Quantum mechanics, emergent spacetime, and participatory physics completely demolish that cold, passive isolation. In a universe where space is built out of entanglement, separation is no longer absolute. The distance between 2 points is not an impassable, fundamental void. It is a secondary, surface-level property. At the fundamental level, everything that has ever interacted remains entangled with everything else. In a universe governed by participatory principles, the observer is no longer a helpless spectator watching an indifferent clock. The act of observation, of interaction, of asking a specific question is a fundamental, creative contribution to how reality manifests itself. You are not an accidental speck of dust sitting on top of a fundamental stage. You are an active node in the complex quantum network out of which the stage itself is continuously projected. You do not live in spacetime. Spacetime is the macroscopic framework that emerges when complex quantum information systems like you interact with the surrounding universe. As the legendary theoretical physicist John Archibald Wheeler reflected toward the end of his long life, we are not only adapters of the universe, we are shapers and builders. In an important sense, this is a participatory universe. We are small, but we are essential. Part 18, the final verdict. Let us return one last time to that sentence that started our journey, the sentence that physicists use when they have run completely out of comfortable classical metaphors. The universe is not locally real. When Alain Aspect, John Clauser, and Anton Zeilinger stepped up to receive their Nobel Prizes in Stockholm in late 2022, they were not being celebrated for discovering a neat theoretical trick. They were being honored for proving that our oldest, most intuitive picture of physical reality was fundamentally wrong. When researchers at Caltech and Google simulated the quantum state dynamics of a holographic wormhole across a processor array, they weren't engaging in science fiction hype. They were demonstrating that the complex geometry of space and gravity can be generated out of pure patterns of quantum entanglement. And when Google's Willow processor resolved a computational problem in minutes that would demand 10 septillion years from the fastest classical supercomputers on Earth, it proved that the raw, non-local computational capacity of nature completely dwarfs the linear, step-by-step limits imposed by classical space and time. These are not 3 disconnected tech headlines. They are 3 clear signals pointing toward a single, overwhelming scientific truth. Spacetime is not the fundamental layer of reality. The universe is not a container filled with solid objects sitting at fixed coordinates in a static void. The universe is a vast, interconnected, non-local quantum system. Space and time are the low resolution, emergent projections, the surface user interface, that allow us to navigate a cosmos far more deeply unified, far stranger, and infinitely more magnificent than anything our classical common sense could ever have imagined. The honest story of modern physics doesn't require sensationalism or embellishment. The cold, verified, laboratory tested truth is already stranger than any fiction we could write. We are not standing at the end of discovery. We are standing at the absolute edge of the stage, looking past the curtain for the very first time. Part 19, the geometry of quantum information and the complexity bound. If spacetime is an emergent surface projected from a deeper quantum reality, a fundamental question immediately arises. What determines the scale, shape, and evolution of that emergent geometry? Why does space feel three-dimensional, continuous, and vast, rather than a chaotic, unstructured mess of random quantum states? The answer that has emerged over the last decade lies at the intersection of theoretical physics and computer science, in a field known as quantum computational complexity. In classical computer science, complexity measures the number of elementary logical operations and or NOT gates required to solve a specific problem or transform a given string of bits into another. In quantum physics, circuit complexity measures the minimum number of elementary unitary operations, simple quantum gates acting on 2 or 3 qubits at a time, required to construct a specific target quantum state, starting from a simple, unentangled reference state. For decades, theoretical physicists treated quantum state evolution as a purely continuous geometric path in Hilbert space. But when Leonard Susskind and his collaborators examined the interior geometry of black holes through the lens of the ADS-CFT dollar correspondence, they encountered a profound geometric puzzle that standard general relativity could not easily resolve. When a black hole forms, its outer boundary, the event horizon, stabilizes very quickly, settling into an equilibrium state in a fraction of a second. To an observer sitting safely outside the event horizon, the black hole appears totally static, featureless, and thermalized. It reaches maximum thermodynamic entropy almost immediately. However, if you use Einstein's equations of general relativity to look inside the event horizon, something astonishing happens. The interior volume of the black hole, the spatial region stretching behind the horizon toward the central singularity, does not reach equilibrium when the outside surface stabilizes. Instead, the interior spatial bridge continues to stretch, grow, and expand continuously for an unimaginably long time. In fact, according to classical general relativity, the volume of a black hole's interior wormhole bridge grows linearly with time for an exponential duration, stretching continuously for a time frame proportional to e to dollars, where s dollars is the entropy of the black hole. For a black hole with the mass of the sun, that interior spatial growth continues unabated for more than $10.70 years. This created an immediate theoretical crisis for the holographic principle. If the outer boundary of the black hole has already reached maximum thermodynamic entropy in a fraction of a second, what physical quantity in the boundary quantum theory corresponds to the continuous linear spatial growth of the black hole's interior for trillions upon trillions of years? Thermodynamic entropy could not be the answer, because entropy reaches its maximum value almost instantly and stays flat. Temperature could not be the answer, because the Hawking temperature remains constant. In 2014, Leonard Susskind proposed a breathtaking solution known as the complexity equals volume (CV) conjecture, which was later refined into the complexity equals action (CA) conjecture. Susskind argued that the physical quantity in the quantum boundary theory that grows linearly over massive timescales is quantum circuit complexity. When you take a complex quantum system of many interacting qubits and allow its wave function to evolve naturally under a non-trivial Hamiltonian, the state does not simply wander around randomly. The quantum state scrambles. It wanders through the impossibly vast landscape of Hilbert space, like continually building up more and more intricate multi-particle entanglement patterns. Even after the system reaches thermodynamic equilibrium, where simple local measurements like temperature or pressure look completely uniform, the underlying quantum circuit complexity keeps growing. It requires more and more elementary quantum gates to assemble the state as time passes. Susskind's conjecture states that the spatial volume of the wormhole bridge inside a black hole is directly proportional to the quantum circuit complexity of its boundary wave function. Text, complexity, prop text. Space, in this precise mathematical framework, is the physical visualization of computational difficulty. The interior of a black hole stretches across immense spatial distances, not because matter is physically expanding through an empty background void, but because the underlying quantum wave function is becoming progressively harder to unscramble. The spatial distance between 2 points in the interior geometry directly measures how many fundamental quantum logic gates separate their respective quantum states. If you want to shorten the spatial wormhole bridge inside a black hole, if you want to bring the two distant ends closer together in physical space, you must perform a complex quantum operation that unscrambles the entanglement, reducing the computational complexity of the state. This leads to a radically new picture of what physical space actually is. Space is not an empty room in which computations happen. Space is the geometric artifact of quantum computation itself. The smooth continuum of space that we take for granted in our daily lives is a coarse geometric rendering of the computational complexity bound of the universe's global wave function. Distance is complexity. Volume is computational history. And gravity is the geometric gradient that results when quantum complexity increases. Part 20, Quantum Error Correction and the Fabric of Spacetime. If space is built out of quantum circuit complexity and entanglement, how does it maintain its structural integrity? Why doesn't a single local measurement or quantum fluctuation instantly tear a giant hole in the middle of your living room? In the real world, macroscopically stable objects remain solid, smooth, and predictable. Space does not randomly snap, tear, or collapse when a particle undergoes a quantum transition. For years, theoretical physicists wrestled with this stability problem in holographic models. In the standard ATS CFT$ dictionary, a single local operator in the flat bulk space, say a particle sitting deep inside the interior of a room, corresponds to a highly non-local combination of quantum operators distributed across the lower dimensional boundary surface. In 2014, three theoretical physicists, Ahmed Almhiri, Xinyu Dong, and Daniel Harlow, realized that the holographic encoding of bulk spacetime in the boundary quantum field theory relies on a sophisticated mathematical mechanism originally developed by computer scientists to build fault-tolerant quantum computers, quantum error-correcting codes, QECC. To understand why this is a revolutionary insight, consider how classical computers handle errors. When a classical computer stores a vital 0 or 1 on a hard drive, cosmic rays, thermal fluctuations, or electrical noise can occasionally flip a bit from 0 to 1 or vice versa. To prevent data corruption, classical systems use redundancy. Instead of storing a single bit as a single physical state, they store it as a logical bit spread across multiple physical bits. For example, writing 000 instead of 0. If one bit flips to 0 and 10, a simple majority vote algorithm immediately detects the error and corrects it back to 00. In quantum computing, error correction is vastly more challenging because of the no-cloning theorem, which mathematically forbids making an exact duplicate of an unknown quantum state. Furthermore, directly measuring a physical qubit to check for an error will collapse its delicate quantum superposition, destroying the computation. To get around this, quantum information theorists in the late 1990s, led by pioneers like Peter Shor and Daniel Gottesman, developed quantum error-correcting codes. They showed that you can protect a fragile logical qubit from local environmental noise by entangling it across a larger network of physical qubits. The quantum information is not stored in any single physical qubit. Instead, it is stored non-locally in the shared entanglement relationships across the entire network. If a local environmental interaction corrupts or destroys one of the physical qubits, the underlying logical quantum state remains completely pristine and recoverable from the remaining untouched physical qubits. Almhiri, Dong, and Harlow proved that the holographic principle uses this exact same mathematical architecture to build emergent spacetime. The bulk gravitational spacetime, the three-dimensional spatial interior filled with stars, planets, and particles, functions as the protected logical layer. The lower dimensional boundary quantum system functions as the noisy physical layer. If you take a point deep inside the spatial interior of the bulk universe and perform an operation on it, that local event is encoded redundantly across multiple overlapping regions of the boundary quantum network. If an environmental disturbance or measurement destroys or corrupts a small region of the boundary quantum state, the interior spatial geometry in the bulk does not collapse. The spatial continuity, the gravitational field, and the localized particles deep inside the bulk remain totally intact and unaffected. The holographic code simply reconstructs the bulk geometry from the uncorrupted regions of the boundary entanglement network. Spacetime is a self-repairing quantum error-correcting code. This realization answered a question that had baffled physicists since the early days of general relativity. Why is gravity so shockingly weak compared to the other fundamental forces of nature? Gravity is roughly $1036 times weaker than the electromagnetic force. A small refrigerator magnet can effortlessly pick up an iron paperclip, instantly overpowering the gravitational pull of the entire Earth. In the framework of emergent quantum spacetime, gravity is weak because it is not a fundamental, localized force operating at the level of individual physical particles. Gravity is an emergent entropic force generated by the robust quantum error-correcting structure of the holographic code. The smooth, gentle curvature of space that we perceive as gravitational attraction is the low-energy geometric response of a fault-tolerant quantum network, maintaining its non-local structural integrity against local perturbations. Space feels continuous, solid, and resilient because it is protected by the ultimate quantum fault tolerance algorithm, a mathematical code that distributes localized physical reality non-locally across the global state of the cosmos. Part 21. The Dark Sector and Emergent Cosmic Acceleration. Once you recognize that spacetime is an emergent fault-tolerant projection generated by quantum entanglement and computational complexity, you are forced to re-examine our greatest cosmological mysteries. Chief among them are dark matter and dark energy. According to the standard cosmological model, lambda text CDM, everything humanity has ever observed, every atom, star, galaxy, gas cloud, planet, and photon, accounts for a pathetic 5% of the total mass energy content of the universe. The remaining 95% is completely invisible, undetectable by electromagnetic sensors, and categorized under two placeholder labels. Dark matter, roughly 27%, an invisible, non-baryonic mass that doesn't emit, absorb, or reflect light, but whose gravitational pull holds galaxies together and stops them from flying apart as they rotate. Dark energy, roughly 68%, and mysterious, pervasive energy density that permeates all of space, acting as a negative pressure that causes the expansion of the universe to accelerate outward over cosmic time. For decades, particle physicists assumed dark matter consisted of undiscovered fundamental particles, weakly interacting massive particles, WIMPs, axions, or sterile neutrinos. Millions of dollars were poured into building hypersensitive underground detectors inside abandoned deep Earth mines, waiting for a dark matter particle to collide with a target nucleus. Every single direct detection experiment has returned a flat zero. At the same time, cosmologists assumed dark energy was simply the cosmological constant, lambda, a fixed baseline vacuum energy built into the fabric of space. But when theoretical physicists tried to calculate the theoretical value of this vacuum energy using standard quantum field theory, they derived a number that was $10 to $120 times larger than the observed acceleration rate. It remains widely recognized as the worst theoretical prediction in the entire history of science. Emergent spacetime offers a radically different perspective. What if dark matter and dark energy are not mysterious physical stuff added into the container of space, but direct signatures of spacetime's emergent entropic mechanics? This line of reasoning was aggressively developed by theoretical physicist Eric Verlinde in his theory of emergent gravity. Verlinde pointed out that in classical thermodynamics, when you add energy to a macroscopic fluid, you change its microscopic entropy and cause an entropic force to manifest, like the pressure that expands a heated balloon. In an expanding, accelerating universe filled with matter, the total amount of available quantum entanglement on the cosmic horizon is constantly shifting. As matter accumulates into localized clusters, like stars, gas clouds, and galaxies, it removes quantum entanglement degrees of freedom from the surrounding vacuum. This localized displacement of quantum entanglement creates an entropic memory effect in the emergent spatial geometry surrounding massive objects. When you compute the gravitational pull of a galaxy using Verlin's emergent entropic framework, an extra non-local gravitational force naturally emerges at large galactic scales, a force that behaves exactly like an additional halo of invisible mass pulling inward on outer stars. You don't need to invent undiscovered exotic dark matter particles sitting inside the galaxy. The extra gravity holding the galaxy together is the non-local entropic reaction of the emergent spatial fabric adjusting to the presence of concentrated matter. Similarly, dark energy ceases to be a wildly calculated, infinitely dense quantum vacuum energy. In an emergent spacetime framework, dark energy represents the baseline rate at which new quantum entanglement relationships are generated in Hilbert space. The accelerating expansion of our cosmic horizon is not caused by an invisible anti-gravity fuel pushing galaxies apart through space. It is the geometric growth that results as the universe's underlying quantum circuit complexity continuously increases over cosmic time. The universe expands because it is computing. The acceleration of the cosmic horizon is the macroscopic manifestation of the global wave function exploring new, unentangled degrees of freedom in Hilbert space. Dark matter and dark energy are not mysterious, hidden ingredients buried inside the spatial box. They are the observational signatures that remind us that the spatial box itself is a thermodynamic emergent projection. Part 22, Quantum Biology and the Macroscopic Interface. If the fundamental world is non-local, non-real, and governed by emergent entanglement networks, why does human experience feel so stubbornly classical? Why don't human beings experience superpositions, telepathic quantum correlations, or holographic wormhole dynamics in their everyday routines? The conventional answer was always scale. Classical physics, we were taught, governs the big, warm, messy, macroscopic world, while quantum physics is strictly quarantined inside the cold, isolated, subatomic microscopic realm. For decades, textbook wisdom insisted that biological organisms, being warm, wet, and endlessly chaotic, could never maintain delicate quantum states. Environmental decoherence, the textbooks claimed, happens so blindingly fast inside a living cell, in fractions of a picosecond, that any delicate quantum superposition or entanglement would be instantly obliterated, forcing the biological system to operate entirely under classical chemistry and Newtonian mechanics. Over the last 15 years, a new discipline called quantum biology has shattered that clean quarantine. Biologists, physicists, and chemists measuring living tissue with advanced spectroscopic tools discovered that biological evolution over 3 billion years of natural selection didn't fight against quantum mechanics, it learned to exploit it. Living systems have evolved sophisticated macroscopic structural mechanisms designed to protect, sustain, and manipulate functional quantum states right inside warm, wet, chaotic biological environments. Consider avian navigation. Every autumn, migratory birds like the European robin travel thousands of miles from northern Europe to equatorial Africa, navigating across featureless oceans and cloud-covered continents with breathtaking accuracy. For decades, ornithologists struggled to explain how these small birds detect the Earth's magnetic field, which is extraordinarily weak, roughly 100 times weaker than a simple refrigerator magnet. The answer, confirmed through detailed laboratory analysis, lies in a protein called cryptochrome, located inside the bird's retina. When a single ambient blue light photon strikes a cryptochrome protein, it triggers an ultrafast electron transfer between two amino acids, creating a radical pair, a pair of highly reactive molecules containing two unpaired electrons sitting in a non-local, quantum entangled state. The orientation of these entangled electron spins is hypersensitive to the alignment of the Earth's ambient magnetic field. As the bird tilts its head, the entangled radical pair alters the chemical reaction rates inside the retinal cells, effectively translating the invisible geometry of Earth's magnetic field into visible patterns of light and dark superimposed onto the bird's vision. The bird is literally navigating across continents by viewing an emergent, non-local quantum entanglement pattern displayed on its ocular interface. Consider photosynthesis. Every plant leaf on Earth absorbs sunlight and converts it into chemical energy with a energy transfer efficiency that approaches an astonishing 99%, a performance level that outclasses any human-engineered solar panel. When a photon strikes a light harvesting complex in a plant cell, it creates an exciton, a localized packet of energy. To convert that energy into chemical fuel, the exciton must travel through a dense, chaotic forest of chlorophyll molecules to reach a central reaction center. If the exciton traveled classically, bouncing around randomly like a pinball from one molecule to the next, it would waste vast amounts of energy as heat, taking a long, inefficient path and losing most of its energy along the way. Femtosecond laser spectroscopy revealed that the plant cell does something far more sophisticated. The exciton doesn't choose a single path. The light harvesting complex creates a long-lived, delocalized quantum superposition. The exciton behaves like a quantum wave, exploring every possible molecular path through the biological protein structure simultaneously. It uses quantum interference to instantly identify the single most efficient zero-resistance route to the reaction center and then collapses cleanly at its destination. The plant leaf executes a natural quantum search algorithm, a biological version of Grover's search algorithm, at room temperature inside a wet cell. These discoveries reveal a profound truth. The boundary between the quantum world and the classical world is not a fixed physical wall defined by scale or mass. It is a dynamic interface governed by how information is structured, filtered, and processed. Living organisms are macroscopic biological engines operating right at the sharp edge of the interface. They are survival systems that have learned to harvest non-local quantum coherence from the underlying fundamental layer, translating it into macroscopic chemical actions that allow them to adapt, navigate, reproduce, and survive. We are not classical biological machines that accidentally popped up inside an indifferent spatial box. We are living manifestations of the interface itself, complex biological architectures designed by evolution to process, translate, and act upon the underlying quantum state of the universe. Part 23, The Engineering of Emergent Space. Where does this leave humanity's technological roadmap over the next century? If you look back across human history, our mastery over the physical world progressed through distinct technological epochs, each defined by our depth of understanding. The mechanical epoch, manipulating macroscopic matter directly through physical force, levers, gears, and kinetic energy. The thermodynamic epoch, manipulating energy gradients, pressure, heat, and internal combustion. The electromagnetic epoch, manipulating the flow of electrons, radio waves, and optical signals across spatial circuits. The first quantum epoch, exploiting the bulk statistical quantum properties of materials to build semiconductors, microprocessors, and lasers. We are now entering the fifth epoch, the epoch of quantum architecture. In this new era, our goal is no longer merely to push physical objects around space, nor to route electrons through silicon traces. Our goal is to manipulate the entanglement structure, circuit complexity, and holographic encoding that gives rise to spacetime itself. What does it look like when humanity learns to engineer the emergent interface directly? Consider the field of metamaterials. For centuries, optical engineers were bound by the natural refractive indices of existing chemical elements. To bend light, you needed glass, water, or quartz. Over the last 2 decades, materials scientists began constructing metamaterials, synthetic structures engineered at sub-wavelength scales with precise microscopic geometries. Metamaterials can bend light in ways no natural element can match, creating negative refractive indices that can route light completely around an object, rendering it effectively invisible to specific electromagnetic frequencies. Quantum metamaterials push this concept directly into Hilbert space by arranging arrays of superconducting qubits, artificial atoms, or topological insulators at nanometer scales. Engineers are learning to construct physical materials that alter the local density of quantum vacuum states. We are beginning to build materials that manipulate the local rate of quantum decoherence, effectively creating quantum insulation that can maintain delocalized, entangled superpositions for extended periods at room temperature. Consider topological quantum computing. One of the greatest practical hurdles facing current quantum computers like Google's Willow or IBM's Osprey is environmental noise. A tiny thermal pulse or magnetic fluctuation can cause a qubit to lose its quantum state, decohere, introducing computational errors. To overcome this, companies and research institutes are racing to build topological qubits using exotic quasi-particles called anyons, which exist only in two-dimensional quantum systems. In a topological quantum computer, information is not stored in an individual particle's spin or charge. Information is stored in the non-local braid patterns created when anyons dance around one another in two-dimensional space over time. You cannot corrupt the stored quantum information by shaking, heating, or disturbing a single physical particle, because the information is not located in that particle. The information resides in the global, non-local topology of the braid network. To ruin the data, you would have to reach in and physically undo the entire multi-particle dance across the entire system simultaneously. Topological quantum computing is the direct commercial application of quantum error correction and emergent geometry. It is software engineering built out of pure non-local topology. Looking even further down the theoretical roadmap, understanding how gravity and space emerge from quantum circuit complexity opens up possibilities that sound like science fiction, but are grounded in rigorous theoretical physics. If space is an emergent entropic projection generated by quantum entanglement networks, then altering the local entanglement density of a quantum system should alter its local spatial geometry. This is the theoretical origin of warp drive metrics like the Alcubierre metric in general relativity. Miguel Alcubierre proved in 1994 that Einstein's equations of general relativity permit a localized bubble of space to contract in front of a spacecraft while expanding behind it, allowing the bubble and the ship inside it to travel at an effective speed faster than light relative to distant stars, without ever breaking the local speed limit of light inside the bubble itself. For decades, the Alcubierre metric was dismissed as physically impossible because it required vast quantities of exotic matter with negative energy density. However, in the framework of emergent quantum spacetime and EPR, negative energy density is simply a localized reduction in the baseline entanglement complexity of the vacuum state. If future advanced technologies learn to systematically manipulate local quantum vacuum state complexity, artificially lowering the entanglement entropy in a localized region of space, they would not be building a rocket that pushes against matter. They would be engineering a localized gradient in the emergent spatial projection itself. They would be altering the user interface directly. Part 24, the ultimate question. What is Hilbert space? As we reach the absolute edge of modern physics, one final, inescapable question looms over everything we have discussed. If space is an emergent projection, if time is a measure of quantum complexity scrambling, if gravity is an entropic error-correcting force, if matter is a localized pattern of non-local entanglement, where does Hilbert space live? What is the ultimate stuff out of which the global quantum wave function is constructed? When you ask a theoretical physicist this question in private, away from television cameras and press releases, they will give you a remarkably honest answer. We do not know. In classical mechanics, if you asked what an ocean wave was made of, the answer was easy: water molecules. In general relativity, if you asked what gravitational waves were made of, the answer was space itself. In quantum field theory, if you asked what light was made of, the answer was excitation states of the electromagnetic field. But when you ask what the universal quantum state in Hilbert space is made of, you reach the absolute end of our current scientific vocabulary. Hilbert space is not a physical place located inside another container. It is an abstract, infinite-dimensional vector space that defines the total set of all possible physical realities that could ever exist. Some theoretical physicists, like Max Tegmark, argue for the mathematical universe hypothesis, the idea that physical existence and mathematical structure are completely identical. In this view, the universal wave function doesn't need to be made of physical material. The mathematical structure is the fundamental reality, and our perceived physical universe is simply what it feels like from the inside to be a self-aware substructure embedded within that mathematical state. Other theoretical physicists, like Anton Zeilinger and Vlatko Vedral, advocate for an information-centric view, summarizing it in John Wheeler's iconic phrase, it from bit or it from qubit. In this framework, the fundamental bedrock of existence is pure information, not information written on paper or encoded in silicon chips, but abstract quantum information, bits of potentiality that can answer binary yes or no questions when probed by an interacting observer. As Vlatko Vedral famously wrote, information is not a property of physical reality. Physical reality is a property of information. In this view, the universe is not a massive collection of physical matter that happens to contain information. The universe is a vast, self-referential information processing system that generates the appearance of physical matter, space, and time as a method for processing, structuring, and experiencing its own internal states. Whether you choose to view this ultimate reality as pure mathematics, non-local quantum information, or a participatory wave function evolving through Hilbert space, one conclusion is completely, unassailably clear. The naive, classical picture of reality is dead, buried, and supported by zero experimental evidence. The universe is not a cold, empty spatial box filled with tiny, isolated mechanical particles sitting at fixed coordinates. The universe is not a deterministic mechanical clock that ticks away in absolute time, regardless of whether anyone is paying attention. The universe is not locally real. The reality we inhabit is a dynamic, emergent, deeply interconnected, non-local quantum experience. Space is the geometry of its computational complexity. Time is the arrow of its scrambling information. Gravity is the fault-tolerant resilience of its quantum error-correcting code. And we, far from being accidental, meaningless specks of dust lost inside an indifferent cosmic void, are participatory biological nodes embedded directly within its global quantum network. We are the universe experiencing its own emergent user interface from the inside. When you look up at the night sky, you are not looking out into an empty, terrifying spatial void stretching infinitely away into cold darkness. You are looking at the macroscopic, low-resolution geometric surface of a non-local quantum state that holds every star, every atom, every galaxy, and every conscious mind together in a single, indivisible, non-local embrace. The classical stage has collapsed, the curtain has been pulled back, and the real show, the deep, non-local quantum reality running underneath, is just getting started.